It's really helpful in the lab to become a master mix master, and using a spreadsheet to help with calculations can help you do it much faster.
So first off, what is a master mix? Basically, if you have a reaction and it has a lot of different components, and most of them are like generic, they're constant for all of the reactions you're going to do. And one of them or a couple of them are different for the different reactions. So you have these generic parts and the unique parts. You can make the generic part enough for doing a ton of reactions for all the reactions you need and a little extra. And then you just add that master mix to the unique part, and this can save you a lot of pipetting time, make things more accurate as well, and to be pipetting as small of volumes. And so these are all really great things about using these master mixes. And today I just wanted to kind of share with you some examples of how you can go about calculating these and using a spreadsheet to help, which is really, really helpful. So the actual calculations that are going into the making these master mixes aren't that complicated. It's all basically based on this whole idea of C1V1 equals C2V2. Sometimes we write this as M1V1 equals M2V2. So in here we have C, when we're talking about it in C terms, C is in the concentration. So you have your initial concentration times the initial volume equals the final concentration times the final volume. Often this concentration is in some sort of molarity, so we can use this M1V1 equals M2V2, and this is the way I learned it. But you can, it's not just for molarity, and so the C1V1 equals C2V2 is like the more generic way to say it. And often, so just a quick note on molarity. So molarity is the unit of concentration that's talking about the number of copies of things in in a volume. And so a mole is kind of like a biochemist's dozen. Instead of meaning 12, it means 6 times 10 to the 23rd, this thing called Avogadro's number. And so if we have 6 times 10 to the 23rd copies of something like molecules of a protein, then it would be 1 molar, but that'd be super. I don't think you can get a protein that high of molarity. You can get salts and stuff, little tiny things that high of molarity. Typically, when we're talking about proteins and that sort of thing, we're dealing more with micromolar and nanomolar and that sort of smaller scales. So this are just like these SI prefixes. So if you're talking milli, that's 1,000th, micro, that's a millionth, nano, that's a billionth, et cetera, et cetera, et cetera. And we can add these to molarity to get, say, 1 micromolar would be 1 millionth of a mole per liter. But anyway, basically this is a really powerful but simple formula, because if we know the initial concentration, so if we know the concentration of our stock, and we know what we want in our desired concentration and our desired volume, then we can rearrange things. We can calculate to get the initial volume that we need to add by just dividing the final concentration times the final volume divided by that initial stock concentration. And so we can set up an Excel spreadsheet to help do this math for us. And so I'll take you through some specific examples, and then also show you how I like to do it if you need a more, you're making your own master mix, like you're designing a reaction, as opposed to, it's a lot simpler when it's just something like reaction components that are given to you by the manufacturer or whatever. They're saying like add this many microliters per reaction of this component with this component with this component. And so a key part, as I talked about, was doing this for like PCR reactions. So PCR, this is where we're making a lot of copies of a strand of some part of DNA. Much more in PCR and other posts, but inside each of these PCR reactions, you're going to have your DNA template. You're going to have the DNA letters, so the dNTPs. You're going to have the DNA polymerase. This is the enzyme that's going to make lots of the copies of the DNA. You're going to have salts and things to keep the DNA polymerase happy. And then you're going to have primers, and these primers are going to be short pieces of DNA that are going to specify where the polymerase should copy, and the polymerase is going to copy in between the primers. So what is this master mix is going to be constant in all of the reactions. And sometimes, especially these days, as we'll get into, like the master mix is often, this is going to come pre-made, but we can also make your own master mix from adding these different components together. Even if the master mix is pre-made, however, you still might need to add water to volume, and we'll get more into this as well. And you might want to say you want to test the same template with different primers. You want to test the same primers with different templates. So maybe you're doing some sort of qPCR, so quantitative PCR, and you're trying to figure out how you're looking at cDNA. So you're looking at what mRNAs were expressed in a cell, and then you want to see, okay, I take this sample, I take this sample, are they different? And so you'd want to test them with the same primers, and so you can make a master mix that contains these primers. So basically you can make a master mix of just this part, you can make a master mix of this part and this part, you can make a master mix of this part and this part. And then you make enough of that master mix that you just have to add this master mix to the unique part. Okay, so let's get a key thing about making a master mix as well is that you want to make enough for it so that you have extra. So I typically like to, if I'm doing a master mix, I like to make, if the ingredients are cheap, I like to do like at least 1.5 extra reactions worth. This way, if you mess up on a whole reaction, you have an extra reactions worth, and that little extra, because when you're pipetting and things, sometimes they can stick on your pipette tip and various things like that. If the reactions are really small, it might even do more than a single reaction extra worth. But as you can see, you can calculate out the amounts that you'll need for each of the different components, make those generic parts together, and then calculate how much of the generic part you need to add to each sample. So the amount of master mix that you are going to add per sample is just going to be the amount of everything minus the amount of the unique part. Okay, so let's get into some actual examples of doing this. So you can set up a spreadsheet to help you do this easier. And so basically, in general, for each reaction, you're going to say, okay, I have this many reactions, but I want to prepare as if there were this many reactions. So this is just the generic sense, and then this is an example, which is for this RNA labeling example. You can basically radiolabel the end of RNA or DNA using this polynucleotide kinase, and you can use radiolabeled ATPs if you want to radiolabel your RNA. Or you can use like fluorescent primers and stuff to get fluorescent labels, various things that you can label with. But when you do this labeling, there's a lot of components in it that are going to be the same for all of your reactions. And then you're going to have your unique part, which is the RNA. So we often say you want to be radiolabeling a bunch of different RNAs so you can then test, compare them. So in each of the reactions, you're going to have your generic things. And so you're going to have like A through D. In this case, it's this polynucleotide kinase buffer, water, hot ATP, so hot is just slang for radioactive, and then this polynucleotide kinase. So this is all going to be generic, and then you have your sample. And so this is to make a 50 microliter reaction. And so in this 50 microliter reaction, the amount of master mix that you have is going to be 48 because you have 2 of your unique, and then the sum of the rest is going to be 48. So this is just in the generic sense. So remember, going back to the number of reactions. So in this case, when I was doing this, I wanted to make 8 reactions. I wanted to label 8 RNAs. So I made 9.5 reactions worth. So in your Excel spreadsheet, you want to put each of these reagents as well as the quantity that you'll need. So this is like a simpler example where basically you're starting where you know the amount of microliters that you're going to need for each thing. Later, we'll look at more complicated examples where we can actually use the initial and final concentrations to figure out what we need. But in this case, we're starting simple and we're just setting up the spreadsheet to be able to calculate things for us. So the final volume, this is just going to be the sum of all the components. And then the amount of master mix is going to be the sum of the components without the unique component. So this is just the sum of the generic components. So this will be your final volume and then your amount of master mix per sample. Importantly, this amount of master mix per sample is going to be constant, even when you're changing the amount of the master mix that you're making and the amount of everything that you're pipetting in. To find out the amount to make for the master mix, you just have to multiply each of these quantities by the amount, by your like multiplication factor, so that taking into account enough to have enough for all of your reactions and the little extra. So this is your prepare as if there were calculation. And so you do this for each of the different components. So when you're using an Excel spreadsheet, you want to make sure that you keep this box constant. So what you can do is when you're on this, you can press, so you could press F4. You can press F4 if you want to, or you can just manually put in these dollar signs if you want to keep this box constant. So this is going to say, so now when I go and I drag this down, it's going to multiply this column by that constant, that same box each of the times. If you don't put those dollar signs in, and then you try to drag down, it's going to try to multiply it down by this box and this box, and you're going to get a bunch of errors. But anyway, okay, so this, then the amount of master mix you're going to make is going to be the sum of all of this. But then remember that for each sample, you're going to be adding 48 microliters of your master mix to 2 microliters of your RNA, because this is per reaction and this is for your master mix. Okay, so that was a simpler example where everything was kind of, we already had the quantities we know that we need. Let's start with another one where we know the quantities that we need ahead of time, but there's more of them. And we're going to make some master mixes with different components missing. So this is an example of a common PCR master mix. This is from like Millipore Sigma's website, and I just kind of adapted it a little. So basically, you have your initial volume. And again, I'll still share this spreadsheet, but this is just to give you examples of how to set up these forms. It's not like this is how you do every single PCR reaction. But so in each of these reactions, you have, so I like to put the total volume. So in this case, the reaction volume is 50 microliters. I have each of the different components, the volume of each component, and then this is just the final concentration or amount. And remember too that like it's important to put the units somewhere. So I like to put the units up here, but don't put like 5 microliters in here because Excel is not going to know what to do with the microliter. Okay, so basically you have all of these different components, and then this is just water to volume. And so in the protocol, it had it like variable amounts depending on how much you add, but to simplify things, I just chose a set volume of in their range so that we then know. And so then the amount of water we add is going to be the sum of the volume, total volume minus all of this. Sometime you'll have something similar, we'll see later, where you can have buffer instead of water, depending on your reaction. So this is telling you how much of each component you're going to have per reaction. But say you want to use the same primer set to test different samples. Now we can make a master mix with everything but that template. So going back to our idea of the PCR, how you have this template and then you have the primers and this all of this other stuff. And so we're making this master mix right now with all of this other stuff, as well as the primers. And then we'll just put in the different template. So going back to our example, now basically we want to make enough of this reaction without that template. So we just take everything but the template. And now this is the amount of master mix we're going to need is the sum of everything except for this template. And this is still for a 50 microliter reaction, and this is for a single reaction. So it wouldn't really make sense to make a master mix for a single reaction. Instead, you want to make the master mix when you're making multiple samples. And so say if you have 4 samples you want to test, now you can make enough from the master mix for 5.5 reactions. So you just need to multiply all those amounts by 5.5. And so you can do this easily in your spreadsheet by setting up a column where you say how many reactions worth you want to make, and then multiplying everything by that. Remember that the master mix volume per reaction is not going to change, and the amount of template DNA per reaction is not going to change, but you are making more of this part of the mix. Okay, but now say you want to use different primers and different samples. So you don't want to have to remix all of this, but you want to not have the primers in there already because you want to put different primers in. So now we're going to make just this master mix. So again, you can just take out what the unique parts, separate the unique parts from the generic parts, and they can offer the generic parts for the amount of reactions that you want. And so now you can see that the amount of master mix we're adding per sample is going down. The amount of these unique parts per reaction are staying constant. And then we're just adapting the amount of these other components, but the amount of these other components you'll see in our master mix, it's staying constant. We're just taking some out and making, so we have less of the generic components overall, but the same amount of each of them because we're making the same amount of reactions. And you can do similar calculations to make master mixes without various components. Just make sure you adjust the volume of the master mix per sample accordingly. So we're adding less of this master mix because more of the stuff is in the unique part. So as I mentioned, many PCR mixes these days come as master mixes already. So basically they have in the mix, they have this part pre-made, and then you just have to add the template and the primers, but you typically have to add water as well because it has a range of water that that you can use depending on how much of your template you actually add. So if your template's really concentrated or if your template's really dilute, sometimes you want to change the amount of DNA you add if you're having trouble with your PCR reaction, things like that. So add to QS to 50 microliters. It's just saying like add it up to the amount of water you need to reach that 50 microliter volume. So to simplify things, if you plan to use 5 microliters of template per reaction, you need to add 18 microliters of water per reaction. So it's really helpful if you want to make a master mix to just like make it so that all of your reactions are using the same volume of template DNA. So if you have one that's more concentrated, you can dilute it down so that they're all, you can add the same amount of each of them so that you can make a master mix that you can use for each of them. Then what you're going to do is basically now we're making a master mix where we have just the master mix and the water. And then we can add in the primer and the template. And so in this case, we just sum up the amount of our generic components to make the amount of master mix we need per reaction. And then we can make enough for the amount of reactions we need simply by multiplying to the multiplication factor. And then we just add the unique stuff separately. We can do similarly to make one without the template, but with the primers like we had done before. But in this case, it's easier because we're starting with that master mix already. Okay, so these are some PCR examples. Let's look at how you can make master mixes for like any reaction. So a lot of times when you're designing a new reaction and things, you're starting from scratch with different components, and you need to figure out the amount of each of these things that you're going to want for your reaction. And so to do this, basically, you want to make sure that you know the concentrations of the various components, as well as the final concentrations that you want. So you have some sort of stock component, stock concentration. You have your final concentration, and then you're trying to calculate the volume you need per reaction, and then the amount that you need for the master mix. And then for the master mix, you can, the amount that you'll have is going to depend on how many reactions worth you want to make. So say you want to make 20 reactions worth, you can then say, okay, make enough for 21.5 reactions. And so in just examples, so I have thing A through thing F, I have the stock concentrations. It can get a little hard when some of your stuff is in micromolar and some is in millimolar and things like that. So just make sure you're watching your zeros. Then you have the final, the stock, the final, and the volume needed. Another note, sometimes you can have it's okay if the units are different. They have to be the same between the stock and the final, but because with the C1V1 equals C2V2 thing, It's really it's the proportions that matter. And so if you have, you can even have like percent and percent, or you can have molar and molar, and this one can be nanomolar and nanomolar. When that happens, I like to, when I put the constant thing, you can actually put the concentration, the units here as well in this column if they're different. But if they're all the same, like if they're all in micromolar, you can stick the units up here. Just a little technical note. So you know the stock concentrations, and you know the final concentration that you want, and then the volume that you need. Well, now you just have to multiply. This is just going back to our C1V1 equals C2V2. So you take your final concentration times the final volume and divide by the initial concentration. And you do this for each of your different columns, remembering to use the dollar sign so that you're multiplying by the same, because you have the same constant volume. Then you have, so you do this for each of the unique things or generic things, and then you have your unique thing. Then the amount of water or the buffer that you have, depending on whatever it is, to make up to that final volume. And you can do this, then for the master mix, it's going to have everything but your unique thing. And so you can multiply each of these values by the multiplication value. What I like to do is I typically create a like to prepare sheet where I take all of these different components and I write it out more simply. So when you have a table like this and then you go to actually pipette, it can be hard to see like what's what. And so I like to copy things down where in a format where I have the thing next to the volume. And then, so then I say, okay, per reaction, I need this much of the master mix and this much of the unique thing. And so here I'm just telling the Excel to copy this cell. If I want to copy this to another spreadsheet, what I do is I copy and then I paste and paste values. This way it's not going to try to calculate things. And so when you're doing this way, it's not going to like, if you're, then you have different boxes and stuff and you get all these reference errors. So I like to copy and paste the values, but remember then if you're changing things here to make sure that you change it over. And so when I make different master mixes and stuff for different components, or maybe I'm making different buffers. So you can do very similar things. If you don't want a master mix, it doesn't have to be a master mix. It can just be like, if you're making a buffer, you can do the same C1V1 calculations. And then what I do is I do like a to prepare sheet. And on that to prepare sheet, I'll copy and paste the values for each of these different things so that I can go and prepare them easier. Another thing to note is that these volumes are really, really low, and this would be really, really hard to pipette these each individually for the different reactions, and I'd have a lot of error. But when you make a master mix, you're pipetting larger volumes. This way, a tiny little like drop is going to be less significant, one of those like teaspoons in a pool versus teaspoons in a teaspoon type of thing, a drop in a pool versus a drop in a teaspoon type of thing. And it's also the pipetting is going to be more accurate. And so it's helpful for the master mix in that sense as well. And then you won't have as much variability in the amounts that you have between the different samples. But speaking back to that, sticking to the pipette, remember that's part of the reason why we make enough volume, we make extra volume. Just a couple more random examples. So you can do things where these are just some examples for some PCR reactions. These and some like a cDNA synthesis example. So when you're making the DNA copy of the messenger RNA for RT-qPCR. So these are some examples that I had found in my notes from when I was doing this before. So you can see I have the per reaction, then I have my multiplication factor, and then I'm multiplying each of the components by that. Yeah, so that's basically it. I will share these pages in case they're helpful for someone, and I hope this video was helpful for someone. Some people had asked me about doing some more example calculations and stuff like that. So I know this was kind of a different post for me, but I hope it was helpful.